Today, I will be talking about the synaptic communication, but first off, I'm going to talk a little bit about the neuron and then zoom in piece by piece to show you exactly how the neurons communicate with one another. Here's a neuron. At this end is the dendrites, which reach out like a branch on a tree that brings the message into the soma, or the cell body. From there, the most powerful message will go into the axon hillock, down the axon to the axon terminals, where it will communicate with another neuron or a muscle. Now that we have an understanding of how the signal travels, let's take a look at what happens while it's traveling down the axon. As soon as the signal hits the axon hillock, action potential begins. From this diagram, you can see that the action potential does not last that long, just a few seconds. The resting potential is when the cell has a negative charge intracellularly and a positive charge extracellularly, and rests at negative 70 millivolts. B shows depolarization, in which the sodium channels open, allowing positive charge inside the cell and negative charges outside. C, repolarization, closes the sodium ion channels and opens the potassium ion channels, allowing the cell to return to its natural state. D, hyperpolarization, is when the cell drops below the resting potential due to the rushing in of potassium. Once it hits this, the potassium ion channels close, putting the axon into a refractory period so it can return to the resting potential. E, the threshold potential, must be reached, which is negative 55 millivolts, in order to fulfill the action potential. There may be a small influx of sodium, but until it reaches the threshold potential, the sodium ion channels will not fully open. Due to the refractory period, the action potential can go in one direction down the axon, meaning it is propagated. Now that we have more information of how it travels, we can take a look at what happens when it reaches the axon terminal. The process in which the neuron exchanges information is called a synapse. As the neurotransmitters travel down the axon and enters the presynaptic neuron before it begins exocytosis. The two classes of neurotransmitters is excitatory and inhibitory. Excitatory, both sodium and calcium go into the cell, causing depolarization, which promotes action potentials. Inhibitory neurotransmitters are when chloride flows into the cell and potassium flows out, causing hyperpolarization, which suppresses action potentials. In order for exocytosis to occur, calcium ions need to be inside the axon terminal. The calcium enters the axon terminal through the L-type voltage-gated calcium ion channels. Once the neurotransmitters are outside of the axon terminal, they are in the synaptic cleft, which is a space in between the axon terminal and the other neuron or muscle. The time it takes for the neurotransmitter to get through the synaptic cleft, or from the end of the presynaptic neuron to the start of the postsynaptic neuron, is the synaptic delay. From there, the neurotransmitter attaches to the neurotransmitter receptor and are now in the postsynaptic neuron. Here are also the ligand-gated ion channels, or the ionotropic receptors, which is allowing the sodium ions into the postsynaptic neuron. And that is how the synaptic communication works.